But you see the problem. There's no useful basis of comparison. Planck was trying to solve this potential for miscommunication in the most scientific way possible. The way he did that was to start with 5 known and well-measured scientific quantities. These are quantities that any scientifically advanced society can measure. The first is the speed of light, which we've encountered before. The second is the gravitational constant, which Newton defined in his theory of gravity. The third is the reduced Planck constant, which is just Planck's constant divided by 2 pi. The fourth is the Boltzmann constant, which arises in thermodynamics and equates the energy and temperature of a gas. The fifth and final fundamental parameter is the Coulomb constant, which arises in electricity situations, most famously in Coulomb's law, which predicts the force between 2 electrically charged objects. Each of those parameters can be measured in any system of units. For instance, the speed of light is about 300,000 kilometers per second, or 186,000 miles per second. But either way, the speed of light has units of length divided by time. What Planck realized was that he could take ratios of these 5 fundamental constants and cancel units, leaving the one unit he wanted for. For instance, the units for the speed of light is length per time. The units for the gravitational constants are length cubed divided by mass and time squared. The reduced Planck constant has units of length squared times mass divided by time. Don't worry if you can't hold that all in your head, neither can I just have to write it down. But if you multiply the reduced Planck constant times the gravitational constant and divide it by the speed of light cubed, the result is a number that has units of length squared. Then you take the square root of that and you can get a quantity with units of length. This is the Planck length. In the metric system, it is 1.6 times 10 to the minus 35 meters. In the American system, it is 5.2 times 10 to the minus 35 feet. And you can repeat the exercise coming up with Planck mass, Planck time, Planck temperature, Planck charge, and on and on and on. Very cool. The numbers one gets in the different unit systems are different, but it's super important to remember that in both systems, they're measuring the same physical length or time or energy. From that, scientists using different systems of measurements can come up with scientifically motivated conversion factors. Planck himself said in his paper to the Prussian Academy of Sciences, "These necessarily retain their meaning for all times and for all civilizations, even extraterrestrial and non-human ones, and can therefore be designated as natural units." The Planck units were definitely an interesting development, but Planck never imagined that they were anything other than a basis of units. He certainly never imagined that they were, for example, the smallest units of length and time. For that, we have to turn to another researcher. Alden Mead is an American chemist who was a professor at the University of Minnesota. In 1959, he had an interesting insight about the role of gravity in very small scales. He spoke with other scientists who didn't find his arguments persuasive. However, after 5 years and countless arguments with referees, he published a paper in 1964 in the journal Physical Review entitled Possible Connection Between Gravitation and Fundamental Length. What his paper did was to consider the effect of gravity on a phenomenon called diffraction, which describes what happens to light when you send it through a small aperture. Because gravity is so incredibly weak compared to electromagnetism, which is the force that governs the behavior of light, its effect is completely ignored in diffraction calculations. But Mead was curious about quantifying gravity's negligible effect. When you scatter a particle of light off another particle, say an atom, the atom's gravitational attraction to the light particle causes an intrinsic uncertainty in the atom's location. Mead applied Heisenberg's uncertainty principle to the problem. Heisenberg's uncertainty principle states that you cannot simultaneously measure the location and motion of a subatomic particle. Mead investigated how Heisenberg's principle would affect the gravitational behavior of a scattered photon. What he showed is that it is impossible to determine the position of an object to a precision smaller than the Planck length. His logic can then be extended to short time durations like the Planck time. I actually talked to Mead back in 2013. I had written an online article about his work. He was an emeritus professor by then, and he had Googled his name and my article came up. We had a long and interesting conversation about his work on the subject, and he was also quite gracious that I hadn't read his paper when it was published, especially since I was only a few months old at the time. It's important to be specific about what Mead's work said. First, it did not say that the Planck length was the smallest length and the Planck time was the shortest possible time. What it did say was that at these tiny distances and times, the laws of physics as we currently understand them all break down. What his work said was at the Planck scales, the effect of gravity can no longer be ignored in quantum calculations. It was later that the scientific community began to think that the Planck scale was somehow a smallest scale. In fact, Mead pointed me to a 2001 exchange of letters in the pages of the journal Physics Today with Nobel Prize-winning physicist Frank Wilczek, who I also hold in high regard. Mead said, "I don't know when or how the transition of the Planck proposal from heresy to conventional wisdom took place, but I can attest that it had not even begun in the mid-1960s. I suspect that it did not really begin to take hold until at least the mid-1970s. So what do scientists claim today? They claim such things as that prior to the Planck time, which is to say in round numbers, prior to 10 to the minus 43 seconds after the Big Bang, time didn't exist. In fact, there are some who claim that at these small scales, time is quantized, where time was 0, then 1 Planck time, then 2 Planck times, like an old school stopwatch where the hand clicked from second to second. In this scenario, there simply isn't any 1.5 Planck times. Similarly, some researchers claim that space is also quantized, coming in discrete chunks of Planck length. If you were super tiny, you could only move in 1, 2, or 3 Planck lengths, but never 1.5. But this idea of discrete space and time is really just a theoretical prejudice and not one we can prove. What we can prove is that at scales like the Planck time, length, and energy, the gravitational effects that we always ignore are no longer ignorable. This has to be the size scale where quantum gravity absolutely must become important, although of course it could become important at larger scales, but it's mandatory at these scales. Furthermore, while it might be possible to look at space at shorter distances, it will require a completely new physical paradigm with new laws, equations, the whole enchilada. Okay, so that's the deal about quantum gravity. It is clear that general relativity breaks in the quantum world. It predicts infinities. And even if we somehow come up with a better theory of gravity, at the Planck length and time, we have to take quantum effects into account. What they will be, we don't know. But what we do know is that the future of quantum gravity will be truly fascinating. Okay, quantum gravity and the Planck scales are the final subjects I want to talk about.